Okay, so far we have been kind of having several important lectures, right? So which we're talking about this type of equation in a vector matrix notation. It looks like x dot is equal to a of x with a certain initial condition. X0 is some x0, right? So we've been talking about this kind of problems so far. Okay, so and the method, okay, so let me kind of remind you that the method is to first find AX is equal to R of X. This is the eigenvalue eigenvector equation, which means that you're just going to look for determinant of A minus Ri is going to be 0. And we've been talking about the case, okay, so when the two roots are real and they are distinct. In that case, you're going to have AX1 is equal to R1 x1. These are two eigenvectors. AX2 is equal to R2 x2. And then the solution is going to look like x of t is C1. Okay, so C1 e to the power of R1t of x1 plus C2 e to the power of R2t of x2. So that's going to be the first case. And then the second case is that R1 and R2 are the real numbers, but they are going to be equal. This is what we discussed in last lecture. In that case, we're going to have that AX is equal to R of X, and then you're going to have A minus the Ri. You're going to look for another Y is going to be equal to the X that you found. So in this case, the solution is looking like C1 e to the power of RT of X plus C2. You're going to use the golden principle T e power RT of X, but you must also accompany with e power RT of Y. So that's what we discussed in the previous lecture. Okay, so that's the general solution. Now we're going to work with the case that R1 and R2 are complex. And if they are complex, you must have lambda plus minus I times mu. So that means the two roots are going to share a common real part and as well as the common complex part, right? So what happens in this case, right? So how are you going to kind of create the general solution in the case when the two roots are complex conjugates to each other, right? So that would be a kind of an interesting question that we're going to kind of resolve within today's lecture. Okay, so within today's lecture. So that's the case we talked about. Today's lecture is complex eigenvalues, right? Complex eigenvalues. So you have lambda plus I mu and lambda minus I mu. So if you look at this eigenvector, so we can mimic the idea that we have a real eigenvalues. So that means you have the complex eigenvalues, right? So let's say complex eigenvalues. So that means, let's say R1 is equal to lambda plus I times mu, and R2 is equal to lambda minus I times mu, right? So now if you look for like A of X is equal to R1 of X. So let's say you want to have the first eigenvector. So let me call it X1, right? So eigenvector, then you're going to see that it means that AX1 is equal to lambda plus I times mu multiplied by X1. So you look at this equation, if A is a real matrix, AX1 should be kind of, but lambda plus I mu is a complex number. So that means a real matrix multiplied by something is equal to complex number multiplied by the vector. If the vector is real, this is never going to be true. Because if the vector is real, the left-hand side will be real, but then the right-hand side will be complex. It's not true. So in the only thing that might let this identity hold is that the vector is complex. How do we express a complex vector? Well, a complex vector simply means that each component of the vector is a complex number. So in that case, you can kind of write this everything as a complex vector where the A is a real vector, B is a real vector. It has a real part and complex part represented as a vector. So let X1 is equal to A plus IB. Is that good for everybody? Okay, so that means you're just going to look for A. Okay, so multiplied by A plus I times B is going to be equal to lambda plus I times mu multiplied by A plus I times B. So that's going to be the case for the X1. Okay, so now we're going to say that we want to look for an X2 such that it is equal to R2 of X2 because R2 is lambda minus I mu. But remember, the R2 is nothing but R1 bar of X2, right? So it's just the conjugacy of R1. So which means that if you have this identity, then you can take a conjugacy. Okay, so that means AX2, you take a conjugacy. When I take a conjugacy of a vector, it means I take a conjugacy of each component of that vector. Okay, so when I take a conjugacy of a vector, it means I'm taking a conjugacy for each component of the vector. This is going to be equal to R1, right? So when you take a conjugacy, it's going to kind of take conjugacy on both vectors, right? So conjugacy, but this is the same thing. Okay, so let's say this is the same thing as AX2 because A is real, right? So A is real, so that the A conjugacy is A. So you just need to take a conjugacy of X2 is equal to R1 of X2 conjugacy. So this conjugacy of a vector means that you take components of each conjugacy of each of the components. So that means if X2 is equal to X21, let's say X2, okay, so we're in dimension 2, so we don't have to really worry about it. It's just two-dimensional vector. Then the conjugacy, it just means X21 bar and X22 bar. So these are conjugacy. So you're going to have this. Now, if you combine this identity, right? So you combine this identity with the original identity here, you get a conclusion that X2 bar is just equal to X1. Is that good? Or one can just say that the second eigenvector is the first eigenvector take conjugacy. Now, if the first vector is represented as A plus IB, where A and B are both real vectors, then the conjugacy is nothing but A minus the IB. Is that good for everybody? Okay, so the conjugacy is just nothing but A minus the IB. So that kind of in summary, okay, so in summary, you're going to have the following situation. Okay, so in summary, it means that if R1 is lambda plus I mu, so the eigenvalues are complex conjugate to each other, then you can see that X1, the first eigenvector, can be represented as something like A plus I times B, but the second eigenvector is that you don't have to calculate the second eigenvector because it can be just obtained by conjugating the first eigenvector. Is that good? So this is a very good scenario. It means that both the eigenvalues and the eigenvectors are conjugate to each other. You just have to kind of find one part, one copy of the plus part, and then the minus part is going to come out automatically. Is a good family? Okay, so in this case, you're not just looking for AX equal to R of X, but the important quantities that you're looking for are the common real part, common complex part, and common real vector and common complex part of the vector. Is that good family? These four quantities are going to replace, so we can say that we use, okay, so we use lambda, mu, and A and B to replace, okay, so to replace the original R1, X1, right, so and R2, X2. So we're using this lambda, mu, A, B to replace the four vectors. So that kind of being said, you're not going to arrive at a formula that you're using R1, so like here, you're using R1, R2, and X1, X2. But now you're not going to use R1, X1, R2, X2. The reason is that they are complex, right? So your equation is real. This original equation is real. You don't want to kind of reach a complex solution. So you want to use only the lambda mu A B to represent your solution. Is that good for everybody? Okay, so you want to use the lambda mu AB to represent your solution, but here you can see that the lambda mu AB is equivalent to R1, R2, X1, X2, because from R1, R2, X1, X2, you can recover lambda mu AB and vice versa. Is that good for everybody? Okay, so therefore, the general solution has a nice formula. Okay, so therefore, the general solution has a very nice formula, which is just given by our formula. Okay, so something like this. Okay, so it is real part. Okay, so as we said before, we say that real part enters the exponential. So you're going to have e power lambda t, right? So let's say plus C2 e power lambda t. Real part enters the exponential. Now the complex part should enter sine and cosine, right? So how is it going to enter sine and cosine? Well, you're going to have cosine mu t and sine mu t a and b. Okay, so So that's going to be cosinuses of mu t multiplied by A minus the sinuses of mu t multiplied by B. So that's going to be like the general case. But here for the C2, you're going to have another copy, which is sine mu t A cosine mu t of B. Okay, so that's going to be sinuses of mu t of A plus the cosinuses of mu t of B. Okay, so now this is an equation. Okay, so this is an identity that you are asked to memorize before you go to the next exam. Okay, so you must memorize this formula before you go to the next exam. They're not going to be kind of provided on an exam as on a separate sheet, but you must know it by heart. Okay, so and it is not very hard to memorize it. You just remember. Okay, so you just remember that e power lambda t is common, right? So that being said, it means the real part enters the exponential and the complex part enters sine and cosine, but you must have both sine and cosine. Remember, it's started with cosine mu t A minus the sine mu t of B, and then on the other side, it kind of flips. It becomes sine mu t of A plus the cosine mu t of B. Is that good, family? Okay, so where A is the common real vector, I mean in the eigenvector, and B is the common complex vector in the eigenvector. So this formula is going to be very important, and you must memorize this formula before you go to the next exam. Okay, so this is the general solution in the complex conjugate case. Is that good, family? Okay, so as a summary, we can say that in this case, we're going to find, okay, so we're going to find, okay, so we're going to find the x12. Okay, so let's say x12 is equal to A plus minus I times B, right? So, and then we're going to have the general solution, which we say that this is C1 e to the power of real part. Remember, it is cosine mu t of A first minus the sine mu t, right? So of the B, right? So the cosine sine plus the C2 e to the power of lambda t. And then you're going to have sine mu t of A, and then plus cosine mu t of the B. So that's going to be the scenario. Is that good, family? Okay, so this completes the whole picture. Like in the three cases, we also have the case for the complex conjugate case. All the cases are comprehensive. So this separate sheet of formulas is something that you must remember before you go to the next exam. Is that good, family? Okay, so and indeed, I have kind of summarized everything by the lecture note that we had for the by the end of the lecture note for the previous section. So, okay, so there's a summary summarizing the whole procedure. Okay, so you said x prime is equal to ax. Then you're going to look for the eigenvectors. You have real distinct eigenvalues. You have complex eigenvalues, right? So and the real repeated eigenvalues, the solution. Okay, so and so that's going to be kind of very important for your upcoming exam. Okay, so for your upcoming exam, please keep this separate sheet of papers strictly to you in order to understand what is going on in this lectures. Okay, so that's kind of the scenario. And as long as we have these formulas, let us practice some examples and see what's happening in practice. Okay, so let's try to solve this following initial value problem. Okay, so let's try to solve this following initial value problem. Okay, so let me take it. Okay, so I will kind of put this formula here. Okay, so we're going to try to solve this initial value problem. So how are we going to solve it? Well, remember here the matrix A is just equal to 0, minus 1/2, 2, and 0. So that you're going to look for determinant of A minus the Ri is equal to 0. You look for the R. So that means this is the determinant of minus R. Okay, so minus 1/2 and 2 and minus R. So that's going to be R squared plus 1 is equal to 0, which means that R is equal to plus minus the I. Is that good, family? Okay, so once you have this, it means that R is equal to I is the first eigenvalue, right? Eigenvalue. And you're just looking for the vector such that A of x is equal to I of x. So this is a complex eigenvalue eigenvector equation. Is that good, family? How do we deal with the complex one? Well, you can just pretend that you are dealing with the real one. So x is equal to x1 and x2. so that you're going to have like 0 minus 1/2, 2 and 0 multiplied by x1 and x2 is equal to I times the x1 and x2. So what you're going to have in the end? It's going to tell you that minus 1/2 of the x2 is equal to I times the x1, and the 2 times the x1 is equal to I times the x2. So you're going to have this. Now, once you have this formula, you can see that I can take, okay, so the first equation says that I times x1 is equal to, okay, 2I times x1 is equal to minus the x2, which is the same thing as the second equation, because you can just multiply both equations by minus I, right? So you multiply this left-hand side by minus I, you multiply the right-hand side by minus I, you can see that these two equations are the same. So this is good news. It means there's actually you just have to pick only one solution, but here the solution you picked is a little bit strange because it's complex. But how you can pick it, right? So if you set x1 to be equal to, let's say, 1, right? So then it means Ix2 is equal to 2, which means x2 is equal to minus the 2 times I. Is a good favorite, right? So you can kind of pick this vector. So that means the vector x, the first eigenvector, is equal to like 1 minus the 2 times I. But this is not enough. According to our lecture, you have to find x1 to be the real vector plus the I times the complex part of the vector. You have to write everything in this form in order to identify A and B. So this is very important for the complex case. You must grasp this case before you go to the next exam, right? So you must understand how to split. This is a vector that has complex components. How are we going to write it as A plus I times B? So this is a little bit puzzling. A lot of people don't know how to work this out, right? So how do we write it as A times I times B? So that's going to be the trick. The trick is the following, okay? So the trick is the following. It applies to every, okay, so every complex vector. You can work it out, is that don't worry about this. Let me write this as 1 plus 0 times I. Each real, no matter it's real or complex number, it must have a real part and a complex part. If it is purely real, it means complex part is 0. If it is purely complex, it means the real part is 0. But don't worry, there must be 1, 0. I write everything in the very standard form. Here's the same thing. So minus 2I is written as 0 plus minus 2 multiplied by I. So that's going to be kind of standard. Once you kind of write everything in such a standard way, you can see that this is a vector 0, 1, and 0 plus another vector 0 and minus 2 multiplied by I. Is that good, family? Now, if you set this to be A plus I times B, you get your vector. So A is equal to 1 and 0, and the B is equal to 0 and minus 2. So you really find it, A and B. And what about lambda mu? Well, the first eigenvector value is I, so it's like 0 plus 1 times I. So you're going to have lambda is 0 and mu is equal to 1. So you're going to have both lambda and mu and A and B. Is that good, family? Okay. So you already, so up to this level, even if you have just worked with the first eigenvalue and the first eigenvector, you have already identified lambda, mu, and A and B. Is that good, family? What about the second eigenvalue? Well, we don't have to work it out because you just see that they are conjugate to the first pair of eigenvalues and eigenvectors. So you may just write it, right? So R2 is equal to minus I, and then the X2, right? The second vector is going to be equal to like 1, 0 minus I times B, 0 minus 2. So you can see that this vector must look like 1 and 2I, right? Instead of minus 2I, use plus 2I. But you don't need it, actually. But what is the actual quantity that you need for your solution formula? Well, you need this lambda and mu, you need this A and B. This is indeed what you need for your solution. So basically, you can finally conclusion that the general solution, okay, so the general solution, right? So the general solution is then found, right? So the general solution is given by x of t is c1 e to the power of lambda t. You can kind of write down the formula, right? So the formula is cosine mu t multiplied by a minus the sine mu t multiplied by b, right? So, and then the second part of the formula is c2 e to the power of lambda t of the sine mu t, right? So sine mu t multiplied by a plus the cosine mu t multiplied by b. So that's going to be the formula. And once you have the formula, remember we have all this data where lambda is 0, mu is 1, and the vector A, okay, so the vector A is equal to 1, 0, okay, so 1, 0, and vector B is equal to 0 and minus 2. So you're going to have all this. Is that good, family? So that means the solution can be found if you just put the data into it. So lambda is 0, e to the power lambda t is 1. So you don't have anything here. C1 of the cosine t, mu is 1, multiplied by 1, 0, minus the sine t, right? So multiplied by 0 and minus 2, right? So that's the first solution. Now the second solution is C2, right? So lambda is 0, so you don't have this. And sine mu t is now sine t multiplied by 1, 0, minus, plus the cosinesis of t multiplied by 0 and minus 2. That's going to be solution. So if you write everything in components, you're going to have C1 cosinesis of t, and you have 0 here. Okay, so then it's plus C2 of the sinesis of t. And then you're going to have like C1, okay, so sine t is minus 2. So 2C1 of the sine t, right? So plus the C2 of the cosine t is multiplied by minus 2. So that's going to give you minus 2 times the C2, okay, so of the cosinesis of t. So that's going to be your solution. Is that good for everybody? Okay, so that's going to be your solution. And you're going to set the solution. This is looking for particular solution. So there is a 0, x0 is 1, 2. So that means the x of 0, according to this formula, is cosine 0, so C1, right? So, and then it's minus the 2 times C2 is equal to 1 and 2. So that's going to give you C1 is 1 and C2 is minus 1. So that means you have already also find the particular solution. Okay, so the particular solution is going to be given by x of t is equal to cosine t minus the sine t, and then it's 2 times the sine t minus, okay, so plus 2 times the cosine t, because C2 is minus 1. So that's going to be the solution. Is that good for everybody? Okay, so in coordinates, okay, so in coordinates, right? So in coordinates, it's just going to tell you that x1 of t is equal to cosinesis of t minus the sinesis of t, and the second component, x2 of t, is 2 times the sine t plus 2 times the cosine t. So that's going to be like the scenario. Is that good for everybody? Okay, so that's going to be like what happens to this complex eigenvalue problem, and it is the following the standard procedure how you are going to solve it. Is that good for everybody? Okay, so I hope you kind of learned in particular how to identify the A and B from a complex vector. If you have a complex vector, you can kind of formally write every component of this complex vector into real and complex parts, and in terms of columns, you're going to split the A and B. Is that good for everybody? This is going to be very important for your upcoming exams. If you don't know how to do this, you're going to have trouble on those exams when you kind of want to distill the real and complex part of the vectors. Is that good for everybody? Okay, so that's going to be kind of very important. That's going to be kind of very important stuff. Okay, so now let us come back to the solution. Okay, so after all this procedure, we have found a solution of cosine t minus sine t, 2 sine t plus 2 cosine t. So now we want to understand in terms of complex eigenvalues, right? So what is the trajectory going to look like? So by trajectory, it means that, okay, so by trajectory, it means that you can let, okay, so I'm going to let the x1 and x2 vary, right? So let's say I let the x1 and x2 vary. Okay, so that means, say you're going to kind of let the x1 and x2 vary. So the t, okay, so suppose the t is going to vary. Let's say t greater or equal to 0. Can you have a picture, right? So of the trajectory of the x1 and x2 in the plane, right? So if t is equal to 0, you're going to start from x1 is 1 and x2 is actually 2. So you must start from 1 and 2. You start from here. Is that good for everybody? But what's the other t varies? What's the trajectory going to look like? How do you deal with this problem? Well, here you can observe that by this trick, you can see that cosine t minus the sine t is equal to x1, and then the cosine t. Okay, so plus the sine t, right? So cosine t plus the sine t is going to be equal to x2 over 2. You're going to observe this. But you can actually use the identity that cosine t minus the sine t square plus the cosine t. Okay, so plus the sine t, you square it. This is going to give you like 2 times cosine square of t plus 2 times the sine square of t minus 2 cosine t multiplied by sine t, right? So let's say cosine square of t, right? So and sine square of t, and then it's going to be plus, let's say cosine square of t, right? So cosine square of t plus the sine square of t minus, so this is a plus, right? So that means, so this is a plus sign, right? So that's plus 2 times cosine t multiplied by sine t. You're going to cancel these two terms. In the end, you use the identity cosine square plus sine square is 1, you get 2. So that means that x1 squared plus x2 squared over 4, this you square it, is going to be equal to 2. Is that good, public? Which kind of further means that x1 squared divided by 2 plus x2 squared divided by 8 is equal to 1. This is nothing but the equation of an ellipse. And what are the axes of the ellipse? The x1 axis started from square root of 2, and the x2 axis started from 2 times the square root of 2. It must be an ellipse, and you can easily check that this ellipse is going to pass the initial point, which is just equal to 1 and 2. So the actual trajectory is like a closed orbit, which is given by the ellipse from this equation. Is that going to okay? So, but how this ellipse is going to rotate? Is it going to rotate in this direction, or is it going to rotate in this direction? It's not clear. But you can see that when t grows from 0, the initial value x1 initially started from 1, and then it's going to be less than 1 because the sign is positive. So you cannot rotate in the clockwise direction. You must rotate in the counterclockwise direction. So the solution is actually rotating in a counterclockwise direction on an ellipse, on a periodic orbit like an ellipse. That's the point. Is that good, family? Right? So we got the solution, which is kind of rotating around the ellipse in a counterclockwise direction. Okay, so that's going to be like the solution to this problem in terms of trajectory. Is that good, family? Okay. So now we have everything we talked about. Okay, so we have talked about everything regarding the second order equations, and they are summarized in this separate sheet, right? So, and there are 3 cases, and for each case we have gotten the formula for the problem, right? So, and we have the origin, which is classified as a saddle point if the eigenvalues have different signs. It is classified as a node if the eigenvalues have the same sign, and improper node if you have repeated eigenvalues, and if you have complex values, and I should say periodic orbits, right? So that means I have to kind of I should kind of add one more. Okay, so let's say periodic. Okay, so periodic orbit, right? So that's kind of a complex conjugate, right? So eigenvalues. Right, so if the eigenvalues are complex conjugates, that kind of comprehensively summarizes what is going to happen in the cases for different eigenvalues. Is that good, family? Okay, so that's kind of a good summary. Here I have listed a few exercises that kind of synthetically, okay, so that kind of synthetically helps you to practice this series of questions regarding 2x2 matrices. Okay, remember they are going to be heavily tested on upcoming exams for this class. If you don't know how to do it, you're going to have a lot of trouble for the upcoming exams. Okay, and also remember that upcoming exams are very important because we are going to have also the final exam. Okay, so this is kind of, please look at these problems. Here I have listed from about 20 such exercises, which covers either of the 3 cases for the real repeated root, real non-repeated root, and complex conjugate root. You have to kind of practice them throughout. Is a good, family? Okay, so that's kind of the thing for this type of problem. Okay, so Now, for the rest of today's lecture, we're going to kind of look at synthetically throughout this class. Okay, so we're going to kind of look back a little bit and see what are the inner connections of these lectures. Okay, so we're going to start. Okay, so we're going to start from a very typical type of equation, mu double dot plus gamma of the u dot, right? So plus k of the u is equal to the external forcing, right? So, but here I'm going to let the external forcing to be 0. So what is this equation? Well, this is a very important type of equation of this class that everybody must grasp. This is the vibration equation. Okay, so this is a vibration equation, and it's a good review of what we have learned so far in this class. Where what is m? M is the mass, right? So what is the gamma? Gamma is the so-called damping constant, right? So, and what is K? Well, K is the so-called Hooke's constant, right? So, or sometimes called the spring constant. Is that good, right? So that's kind of what describes the vibration, and you must also remember that U is the relative position, right? So, is the relative position with respect to equilibrium, right? So it's the relative position with respect to equilibrium, and you must have the fact that the downward direction, okay, so downward direction is going to be positive. The downward direction is positive. Is that good, family? Okay, so that's going to be kind of a brief review of what we have learned so far. Now, how do we solve this equation? Well, previously, we were kind of working with the characteristic equation, right? So you should work with the characteristic equation, which means that mr squared plus gamma of r plus k is equal to 0. You're going to solve for the r1 and r2. And based on the r1 and r2, you're going to have a solution. So y of t, so u of t, right? So you can have the fact that u of t is c1 e to the power of r1 of t of, right? So, and then plus the c2 e to the power of r2 of t. This was the case when r1 is not equal to r2, but r1, 2 are both real. Is that good? But you can have other cases such as c1 like the e to the power of rt plus c2 t times e to the power of rt. This is the case when r1 is equal to r2, but both are real. Is a good, right? So let's say is equal to r. And you can also have c1 of cosinuses of mu t, right? So so that kind of is going to give you like c1 e to the power of lambda t of cosinuses of mu t plus c2 e to the power of lambda t of sinuses of mu t. Here it means that r12 is lambda plus minus I times mu. So there are 3 cases, right? So this is kind of a brief review of what we have learned so far regarding the vibration equation. Now here I'm going to kind of view this vibration equation from the point of view of systems of differential equations. So what should I do? Well, here I'm going to say that mu double dot plus gamma u dot plus k of u is equal to 0. I'm going to turn this equation into a system. So this is very important, and we have been talking about it before the first lecture of this chapter when we talk about system of differential equation. So how are we going to do that? Well, you're going to set, so you're going to set the x of t, right? So to be equal to like u and v, right? So you're going to set u and v, where v is supposed to be u dot. Is that good, right? So that's kind of how you turn, so we've been talking about at the very beginning of these lectures, how you turn a system of differential equation, how you turn a higher order equation into a system of differential equation. You must set derivatives to be the new variables, right? So this is very important, and you're going to be tested about it on your exams, okay? So this is going to be very important. And once you have v is u dot, you are going to see that, let's say, u dot is equal to v. But what is v dot? Well, v dot is actually u double dot. Is that good, family? Right? So because u dot is v dot is u double dot. But u double dot can be solved from this equation. It's minus gamma over m of the u dot minus k over m of the u. So that's going to be the scenario. But u dot is v, so that's minus gamma over m of the v minus k over m of the u. So if you write everything like more standardly, you're going to see that u, okay, so I'm going to say that let's say u dot, right? So and v dot, right? So this whole object is equal to something like v, right? So u dot is v, and v dot is equal to minus k over m of the u minus gamma over m of the v. So you're going to have this. And now this object can actually be written as a matrix multiplied by uv. What is the matrix? Well, it's 0, 1 because there's only a v. And then it's minus k over m and minus gamma over m. Is that good, everybody? Okay, so this is kind of the connection between the second order equation, right? So higher order equation, as well as the system of differential equations. You can just set it everything like this. You obtain like the matrix A is kind of looking like this. So this is very important. Okay, so very similar exercises. It will largely, I mean, very probably will happen on your next exams. Okay, so that's kind of very important. Once you have this matrix A, you can see that the whole system is now written as x dot is equal to A of x, which is like the second order linear system of equations in vector matrix form. That's the same thing as we just saw before. Is that good for everybody? So we would like to solve this equation from the eigenvalue, eigenvectors. So that means you want to look for like A of x is equal to R of x. Is that good for everybody? Right? So what's this equation? Well, you can look for determinant A minus the Ri is equal to 0. Remember, the matrix A has the form 0, 1 minus k over m and minus gamma over m. So that's 0, 1 minus the k over m and minus the gamma over m. So that's the matrix A. So that means determinant of A minus the R times I is the determinant of minus R and 1 minus the k over m and minus the gamma over m minus the r. So you're going to have this matrix, and you calculate determinant is going to be r squared plus gamma over m of the r plus the k over m, right? So that's going to be determinant because you just cross product this one with this one, and you minus this one with this one, right? So, but there's a minus sign already, so there's a plus. And this is nothing but 1 over m, which is the mr squared plus the gamma of r plus of the k is equal to 0. You're going to look for this. Now, if the mass, since, okay, so let's say since the mass is positive, you're just going to have mr squared plus gamma r plus k is equal to 0. And what is this equation? Well, this equation is nothing but this equation, which is the original characteristic equation that we learned in our previous chapters. Is that good? Okay, so this actually tells us that the characteristic equation that we looked for in our previous chapters, right? So when we talk about second order equation and vibration problem, this characteristic equation is nothing but looking for the eigenvalues, right? So the characteristic roots that we talked before are nothing but the eigenvalues of this matrix vector notation. So this is the interconnection between different lectures of this course, which I think is kind of a very interesting and very important to reveal at this point. So this equation is just the characteristic equation. Okay, so this equation is just the characteristic equation. And if you remember several lectures ago, when we talk about determinant A minus Ri is equal to 0, sometimes we also call it the characteristic equation. Okay, sometimes it's also called the characteristic equation. Is a good number. That's why it is called the characteristic equation, because if you write this equation, you're going to just reach this equation. Is a good family? Now we can also use our theory for higher order equations. Okay, so let's say you can find Ry is not equal to R2 and R1, 2 are real, right? So in this case, according to our theory, you're going to look for a vector, right? So you're going to look for a vector. So basically you're looking for AUV is equal to, let's say, R1 of the UV, right? So, and then you're going to look for AUV, right? So let's say U1, V1, U1, V1, and U2, V2 is equal to R2 of the U2 and V2. You're looking for eigenvectors. Is that good, family? Okay, so you can kind of resolve this eigenvalue, eigenvector equation. Okay, so eigenvalue, eigenvector equation But then you're going to have these solutions. Okay, so now how are you going to find these solutions? Well, it depends on the discriminant. So if this is the case, it means the gamma squared minus 4 times km is going to be positive, right? So as long as the discriminant is positive, you're going to find a solution, I mean, two eigenvectors, and you combine them into two eigenvectors. Okay. Now I leave to you as an exercise to double check that in this case, you see what we are looking for. Are we looking for the V? Well, the V is just an auxiliary. So V, or sometimes we call it auxiliary. V is just an auxiliary variable to make your equation into systems. But you're looking for is a U. Okay, so now you can see that in this case, after a lot of effort, okay, so I'll leave to you an exercise, you're going to see that U of t is nothing but C1 e power R1t plus C2 e power R2t. Okay, so which is going to agree with the solution theory that we talked about in our previous lectures. Okay, so I leave to you as an exercise to double check this. And similar thing is going to be happening. Okay, so similar thing is going to be happening if you have like the complex roots as well as the real repeated root case. Okay, so this is kind of an example that just tells you that what we have been talking about before about this 2x2 system of equation is actually connected to what we have been talking about in our previous chapters when we talk about vibrations or general higher order differential equations. Is that good, everybody? Okay, so this is kind of a nice example that everything is interconnected. And if you kind of carefully analyze this example, you learn a lot because it kind of tells you how we're going to change a higher order equation into a system, and from the system, how we're going to solve everything. Okay, so, and it also points out the interconnection that the characteristic equation for the eigenvalues is the same thing as the characteristic equation for the characteristic roots that we have learned in our chapters for higher order equations. Okay, so this is a good interconnection between the different types of parts of the class during the semester. Is that good for everybody? Okay. So let's up to here. So I have finished everything about this systems of, I mean, the x dot equal to a of x solution theory about this. Okay, so now we can see that everything so far. Okay, so everything so far is about x dot equal to a of x. This sometimes we call it the homogeneous equation, right? So this is sometimes we call it the homogeneous equation, right? So that means that so far we have been kind of dealing with the homogeneous equation of the system of differential equations that in a homogeneous form. Okay. So now let us come back in our next lecture to continue with discussion and might be talking about inhomogeneous, non-homogeneous equations. Okay. So that's what I want to say for today's lecture, and let's stop here. And I'll see you in the next lecture. Okay. So see you in the next lecture.